everyone. In previous classes already we have studied about the postulates of an Bohr's atomic model. So what he says to us through his postulates. So see here, once I wish to recap that postulates. First postulates he says to us, when the electrons are revolve around the nucleus in a fixed circular path with a fixed energy, these are called as an orbits. So this is his first postulates. And second one, what he says to us, the electron does not change. Electron does not change. Electron does not change its energy with a time. And the third postulate, it is a very important postulates to us. What he says, when the electromagnetic radiations are absorbed or emitted by the electron, then what happens? The transitions takes place in between the two stationary states or two stationary levels. Means when the electrons are emit the radiation or frequency of radiation or absorb the radiation, then what happen? The electrons are takes excitement and then they jumps lower energy to higher energy level. Then what happen? The transitions takes place in between two states of energy levels. And then the fourth one, what he says to us, that is the angular momentum of an electron is equals to, the angular momentum of an electron is equals to integral multiple of h by 2 pi. So he says about his idea of structure of an atom. And to say about the third postulates, he thoroughly studied the hydrogen line spectrum. And he studied all about atomic spectra and thoroughly studied about hydrogen line spectrum, and then he gave us this postulates to us. Then in today's class, I wish to explain about that atomic spectra, means hydrogen line spectrum. Hydrogen line spectrum. So see here, we take a hydrogen gas here. When we discharge electricity, or we supply the energy to this hydrogen atom, then what happened? In this gas, we have a grow together of hydrogen atoms, or lack together of an hydrogen atoms, or grow together of an hydrogen atoms. So what next? Then what happened there? See here, when we supply the electricity or when we supply external energy to this hydrogen gas, then what happened? The hydrogen gas splits into like hydrogen atoms. Then next, these hydrogen atoms are having a nucleus and they are having electrons around us. So all this set is having in all hydrogen atoms. Then what happened? Then that these electrons are absorbed the electromagnetic radiation, absorbed the external energy. It got extra energy to it. And then what happened? This electron jumps from their original states to higher energy level. So see here, this is our electron. It got energy. When we apply external energy to it, then what it happened? It become a excited state, and then it jumps from lower energy to higher energy level, ground state to higher energy level. So its original position is called as a ground state. So it jumps from ground state to higher energy level. Then what happened? It become unstable here. Then what happened? It emits the radiation. and lost its energy and lost its energy. Again, then what happened? It come back to its ground state or its original state. So this happens in a hydrogen spectrum. So see here, what do you mean by hydrogen line spectrum? Once again, I wish to say here, in previous class already I told you about the emission spectra and the line emission spectra. This hydrogen line spectrum is also belongs to that line emission spectra. So see here, we taking a hydrogen gas and we are heating this hydrogen gas, or we apply the electric discharge to this hydrogen gas. Then what happened? The atoms absorb the radiation. Then it goes lower energy states to higher energy states. Then what happened? They are unstable here. They become unstable in their higher energy level. Then they loses the energy in the form of radiation. And then again they come back to its original position. This radiation, when we are passing through the prism, then what happened? It shows the spectrum to us. We got at the photographic plate the colored lines with a dark background. So this is our hydrogen line spectra. So see here, how much energy we applied to this, how much energy they absorb. Depend upon that, we got a different line series of hydrogen line spectra. We got different line series in the hydrogen spectrum. So what are that line? How we got that lines, and what are that line we are studied forward. So see here. Consider this is a nucleus of our hydrogen atom. So these are the shells of an hydrogen atom. So number 1, 2, 3, 4, 5, 6. So these are shells of our hydrogen atom. So up to we have a infinity number of shells. So in the first shell we are having our electron. When we apply the electricity to it, then it absorbs the electricity and it gains the energy, and it jumps from its lower energy to higher energy level. And these are shells named as a n equals to 1, 2, 3, 4, 5, 6. So n1 is, or n is equals to 1 is its lower energy state. It may be jumps from n1 to n2, or it absorbs a higher energy. It may jumps from n1 to directly n3, or it may be jumps from n1 to n4 or n1 to n6. So like this, when it jumps from its higher energy state, is that electron is a stable? No, it feel uncomfortable. It is in the state of an unstable. Then what happened? It emits the radiation. Again it comes back to its original position. So see here, the electron comes to its original position from 6th level to 1st level, or from 5th level to 1st level, or 4th level to 1st level, 3rd to 1st, 2nd to 1st. So like this, we got a series of lines, or we got a different transitions. So see here, by the spectra we got the series of lines in spectra. So see here, so this is a one set of transition. So these are all the lines, are belongs to same frequency or same energy in our electromagnetic spectrum, like ultraviolet region, So these set of series we called Lyman. These set of series we called Lyman series. So like this, if the energy level, or if the electron comes to its second shell, its second energy level, and then by the fifth position it comes to second, by the fourth position it comes to second, by the third position it comes to second. So like we are having again one set of series of transactions is there. Again we are having a set of or a series of lines. This series of line belongs to visible region, and these lines are called as an Balmer. L is silent here, Balmer series. And next some kind of set of lines we are having it. So these set of lines we are called as an Paschen series, and these radiations frequency and energies matches with infrared region. So like some sets again we are having here. So those are bracket series. These are also we find in infrared, means far infrared region. So some away from the infrared region, but they are belongs in a infrared region, so I called as a far infrared region, bracket series. And next series we got here, those are fund series or P-fund series. They are also belongs to the far infrared region. So neatly I wish to explain here by the diagram. These are our energy levels. So this is our first energy level, that is N1, and it is our second energy level N2, and third energy level N3, fourth, fifth, sixth, seventh. As the number of shell increases, their distance also decreases. As the number of shell increases, their distance decreases. Just remember it, because the difference between the energy is less, here. So it is our, when electron jumps from to its N1 state, it is our Lyman series. So it is our Lyman series. Next, the electrons coming their second energy level from their higher energy. So these are N4, 5, 6, 7. So this is our Balmer series. These are available in visible region. Visible region. And next one is Paschen series. Next one is Paschen series. The electrons are jumps from higher energy to its N3, means its lower energy level. So this is our Paschen series. Paschen series. And next one is higher energy to its lower energy, means N4 energy level. These are our bracket series. Bracket series. And next one is fund series, means higher energy to their N5, means lower energy level. This is our fund series. So see here, to the Lyman series, their ground state means N1 is equals to 1 and N2 is equals to 3, 4, 5, 6. And next, to the Balmer series, N1 is equals to 2, because it's their ground state, their lower energy state is second shell, it is 2, and then N2 is equals to 3, 4. Next, to the Paschen series, their ground state or their N1 is equals to how much? Their N1 is equals to 3. To the bracket series, their N1 is equals to 4 and here N1 is equals to 5. Just remember these values. Here. And next one is, these line spectrum are expressed in terms of a wave number. These lines are expressed in terms of a wave number. Just see the calculation here. The energy gap between two energy state level is delta E is equals to En2 minus En1. N2 means this is higher energy level N2 and N1 is its lower energy level. Then what happened here? Already you know that En is equals to, we have one formula, that is 2 pi square k square m e raised to 4 into z square divided by n square and h square. So you remember this formula, 2 pi square k square m e raised to 4 z square n square h square. In the place of n, can I put the value of N2, because N2 level we have to mention here. Then minus, here also minus, then minus of 2 pi square k square m e raised to 4 into z square divided by, again in the place of n I put N1 value, N1 square and H square. And next, minus into minus, what happened? Plus. Just I write this equation here, 2 pi square k square m e raised to 4 into z square divided by N2 square and H square plus 2 pi square k square m e raised to 4 into z square divided by n1 square h square. Then just observe here, the delta E is equals to 2 pi square k square m e raised to 4 and z square. Here also we are having 2 pi square k square m e raised to 4 into z square. And next, in the denominator h square, and here also we are having h square. Then I wish to take this term as a common. Then what happened here? 2 pi square k square m e raised to 4 into z square divided by h square. Then what will be the remaining term? I mentioned here 1 by n2 square minus 1 by n1 square. That's it? Clear? Okay. Then the delta E, the energy of photon, already you know that E is equals to h mu. Then in the place of delta E, can I write h mu is equals to then 2 pi square k square m e raised to 4 into z square divided by h square, then 1 by n2 square minus 1 by n1 square as usual. And then see here, mu is equals to c by lambda. Already you know that. So then I mentioned here 1 by lambda, then what happened? H and c. H into c into h square. Then what will becomes here? 2 pi square k square m e raised to 4 into z square divided by h into h square into h cube into c, that is h cube into c, into 1 by n2 square minus 1 by n1 square. Then so when we putting the value of this constant term, we got one value, and that value is called as a Rydberg constant. This value is called as a Rydberg constant. So I mentioned that Rydberg constant, that is R into z square 1 by n2 square minus 1 by n1 square. Then 1 by lambda is equals to mu bar, means wave number. Already I told you these lines are expressed in terms of a wave number. Then R is a Rydberg constant. Then what is the value of R? Means Rydberg constant is 10.9677 centimeter inverse. So then R into z square 1 by n2 square minus 1 by n1 square is our equation. Just it is very easy to remember. See here, 10, one step backward, 10, 9, and then these 3 digit 10, 9, and next take a 6, one step forward, 7, 7. So 10, 9, 6, 7, 7. 10, 9, 6, 7, 7. So this is very easy to remember this value. It is our Rydberg constant. And next we write this equation in the form of electron volt per atom, that is 1.36 into z square 1 by n1 square minus 1 by n2 square electron volt per atom. Electron volt per atom, that is delta E is equals to. So we can apply this formula also depending upon their units. We have applied different types of formula, means different type means little bit the value of this Rydberg constant is difference for different unit. So we are applying this formula. So we have to calculate our numericals based on this hydrogen spectrum or Bohr's atomic model of an atom.